Okay, so we've looked at solving linear equations. We looked at solving rational equations that tended towards being a linear equation once we cleared the fractions. We looked at quadratic equations, solving them in all different types of methods. Factoring is the easiest if possible. If not, then if it's in a particular form, like with a perfect square, we could use the square root method. We can manipulate our quadratic equation to be a perfect square by using the completing the square method. And then we saw that we derived the quadratic equation by completing the square on a generic quadratic, ax squared plus bx plus c equals 0. And so now we looked at complex numbers, which is square root of -1 would give us an imaginary number. And so that's a complex number. And now we're jumping into solving radical equations. This next section that we're looking at is not just radical equations, it's just solving all different types of equations. So it might be equations, again, that don't look like a quadratic, but we might be able to manipulate it to look like a quadratic to help us solve. So I want to kind of go over a couple of things that you got to remember in order to, this will be really helpful in this section. So rules of exponents. So I just kind of want to recall a couple of things that will be helpful. So rules of exponents. If you have some same base, that's bizarre, and you're multiplying, so like b to the m times b to the n, this is equal to b to the n plus n. I don't want to draw with my finger. I'm not sure if I'm liking this version of OneNote. Yeah, I'm going to go to my version. Sorry, guys.
Well, your drawing's impressive for a computer.
Well, I get to use my pen. If I was using a mouse, it wouldn't be like that whatsoever. And I can draw on my tablet, so that's what is very helpful. We're college algebra, we're here, we're doing radical equations. Okay. So the other thing that we want to look at for radicals, or sorry, rules of exponents, is that if you have b to the m, so you have something raised to a power, and then you're raising that to a power, so b to the m times n, this is equal to b to the m times n. So we're going to be using this fact actually to help us clear the radicals. And so another rule that you need to remember is if you have a radical, so let's say that this is the nth root of b raised to maybe the m power, we can rewrite this in exponential form without the radical. And so this is the same thing as b raised to the, so it's the power here is the numerator, and the index of the radical is our denominator. So this is the same thing as b raised to the m over n power. So going back and forth is helpful. Okay. So if you jump in and you find an equation and you see a radical in that equation, the first step that we want to do to solve an equation with a radical is we want to isolate the radical on one side of the equation, if not already done so. So solving radical equations. So if there's more than one radical, then we just want to isolate one of them on one side of the equation. So first, isolate one radical. On one side of the equation. And so once we've done that, we're going to use this property above to get rid of the radical. And if we do power to power, it's multiplication. So basically, if you have a square root, to get rid of the square root, we want to square both sides. If we have a cubed root, then we want to cube both sides. If we have a sixth root of something, we want to raise both sides to the sixth power. So you're going to raise both sides of the equation. By the index of the radical. So that's just the terminology, that index. That's just what root you're taking of the radical. Okay. So be careful. If you have more than one term on that one side that doesn't have the radical and you raise that side to a power, you're going to have to distribute. You can't just raise each term to that power. That's wrong. And you won't get very many points on a test from me for doing that. So a lot of people think that the quantity a plus b quantity squared is just a squared plus b squared, which it's not. You can't just do that. You have to do a plus b, that quantity all times a plus b, which ends up being a squared plus 2ab plus b squared. Okay. But anyways, that's just a side note. So you raise both sides by the index. That clears hopefully the radical, but if there's more than one radical in there, there's sometimes it will occur that the radical doesn't disappear, or one of them doesn't disappear. So you're going to repeat steps 1 and 2 until there's no more radicals. So there are no terms with radicals. And then we need to look at what type of equation are we left with once those radicals are gone. Is it a linear equation? Then we would solve it, you know, how we proceeded with solving linear equations. If it's a quadratic equation, then you get to figure out which method you want to use to solve that quadratic equation. And so then solve. So this is where we have to really be careful. If you raise both sides of an equation by an even power, we may get values that actually aren't solutions to our equation. They're called extraneous solutions. And so we have to, you must check your answers. If you raise both sides of the equation by an even power. Okay. So you may get what is called extraneous solutions. So again, extraneous solutions are solutions that actually really aren't solutions. We have to exclude them from the solution set because they don't work when we plug them back in. Okay, yay, we get to do the fun part. We get to do the math. Let me just do this. Okay, which one looks really nice and I would call it juicy. The fourth root of x squared plus 16 is actually equal to the square root of 5. Okay, so we actually have two radicals, and I notice actually the indexes are not the same. And we need to solve for x. So we want to clear that radical. And this is where I was saying that if we rewrite this, sometimes it's helpful to rewrite this. If we rewrote this, the fourth root is the same thing as a 1/4 power. So in here we have x squared plus 16. And this is equal to, let's just rewrite the square root of 5 right now without the radical. So this is the same thing as 5 raised to the, if the index is not shown, that's 2. So this is 1/2 power. Well, the whole point of this is to get x by itself. So we really need to get rid of that 1/4 power. And so to get rid of the 1/4 power, we're going to use the fact that we can power to powers multiplication. So we're going to raise both sides by the index of this fourth root, which is 4. And if we do something to one side of the equal sign, we have to do it to the other side. So we're raising the other side to the 4th power. Okay, so 4 times 1/4 is 1. So that clears that radical, and we're just left with x squared plus 16. And this is equal to, again, power to power is multiplication. So 4 times this 1/2, that gives us 2. So this would give us 5 squared. So notice it's quadratic, but I also noticed that it's kind of also looks like a perfect square. So there's two ways we can do this. So we have x squared plus 16 equals 5 squared is 25. We can isolate the square and take the square root of both sides, or I can set this equal to 0 and factor. Either way, we're going to get the same result. The only thing I'm worried about is when I use the square root method, or students do, they forget to put the plus or minus in front of that radical. And so sometimes you're missing half of the solution. So let's subtract 25 on both sides so we don't maybe do that. And if you do that, you get x squared. And 16 minus 25 is -9, is equal to 0. So looking at this, this is a difference of squares. I would factor it, x minus 3, x plus 3 equals 0. And so this is when x is equal to 3 and when x is equal to -3. So setting each piece equal to 0 and solving. So again, we need to check. We rose both sides to the 4th power. And so we're going to go back into our original equation, and let's first check x equals +3. So let's go back to the original equation. We have the 4th root. Wherever we see an x, we're going to put a 3. I'm just going to put parentheses now where that x is. Squared plus 16 equals the square root of 5. I'm putting in the 3. So I have the 4th root. Well, 3 squared is 9. 9 plus 16 is 25. This is equal to the square root of 5. So how can I manipulate that to show that? And I'm putting a question mark right here. This is actually what we're checking. Well, remember 25 could be rewritten as 5 squared. So this is the 4th root of 5 squared. If I go back in and I rewrite it at first in exponential form and reduce that fraction, and then write it back as a radical, I can see I would get √5. So this is the same thing as 5 squared raised to the 1/4 power. Power to power is multiplication, so that's 5 to the 2/4 power, which is 5 to the 1/2 power, which is the square root of 5. Okay. So yes, positive 3 is a solution. Can we tell if negative 3 is a solution or not without having to go back in and plug that in just like we did with positive 3? Why or why not?
Yeah, because a negative squared is a positive.
Right, exactly. So if we go back in and we plugged in x equals negative 3 right here and we squared it, we would still get back positive 9. And so we would get the same result. And so we're okay. And so we do, both of them work. And I'm looking for that on an exam. There's going to be a lot of times in this, just like we saw with the rational equations, that maybe our answer doesn't work because it could have set our denominator equal to 0. And here's another place that we have to check because we might get some value which actually gives us a negative or doesn't give us the same result when we plug it back in. Let me just put that there so if you need to see. Okay, that one was fun. That's an unusual one I haven't seen before actually, but it goes through a lot of the rules. And important rules that you're going to be using things a lot where in calculus where you're changing and using properties of exponents a lot. So what about the square root? We have 10 plus 3 and the square root of x, and that's all underneath that one main radical. And this is equal to the square root of x. Okay, so first step is to isolate one of the radicals, again, already done for us. We can raise both sides of the index of our radical, and this would be so we could square both sides. So that would get rid of this main radical on the one side, leaving us with what's underneath, which is called the radicand, and that would be 2 plus 3 square root of x. This is equal to, well, over here, when I square the square root of x, that just also gives me just x. Okay, so I still have a radical in my equation, and so the step said if I still have a radical, now I want to repeat the process. So I want to isolate this radical, and so let's subtract 10 on both sides of our equation. Well, those aren't like terms on the one side, and so we're left with 3 square root of x is equal to x minus 10. So normally, if I have a coefficient in front of that radical, I would think about dividing everything through by that, but then I'd have to deal with fractions on the other side and distributing, and I don't want to do that. So I'm just going to leave this piece in here, and I'm going to go back to a rule again of exponents that says if you have two things that you're multiplying together, so we could have a times b maybe to the nth all to the m power. If it's strictly multiplication in here only, can we do this? We get a to the m, b to the n m. Power to power is multiplying. Think of this as a power of 1, so 1 times m is m. Okay, so I'm going to use that property, and so I'm going to have to square each piece of that 3 root x. And I'm going to square both sides so I can get rid of that radical. So I have 3 squared, which gives me 9. And I have square root of x squared, which gives me just x, is equal to, and so this is where I have to distribute x minus 10 times x minus 10. And this is where I would get a little upset that you did x squared minus 100 or plus 100 there, if you did. So distribute x times x is x squared. X times negative 10 is negative 10x. Negative 10 times x is negative 10x. And negative 10 times negative 10 is plus 100. Okay, no more radicals. Looking at the type of equation I'm left with, it's quadratic, so I want to get everything to one side, combine like terms. Okay. So right here, I notice that this right here is negative 20x. And I'm going to be subtracting 9x on both sides. And so if I subtract 9x on both sides, we get x squared. Well, negative 20x minus 9x is negative 29x. Plus this 100 equals 0. So I'm looking for two numbers I can multiply to give me positive 100, but add to give me a negative 29. And I can do that because my coefficient right here is in front 1. So 25 times 4 is 100. But if I have them both negative, when I add them, I get negative 29. So I'm going to do negative 4 and negative 25. So I'd have x minus 4, x minus 25 is equal to 100. So I'm looking at when is x minus 4 equal 100? I'm sorry, when is x minus 4 equal to 0, which is 4? And when is x minus 25 equal to 0? And that's when x is 25. Okay, so again, we got to check because I rose both sides to an even power. So you're going back to the original one before we did anything to it. And wherever we see an x, let's first try 4. So we have 10 plus 3 square root, and we have an x there. I'm going to replace it with the 4. Is this technically equal to the square root? Do you see an x there? Replace it with a 4. Oops, I wanted the green. So order of operations, simplifying, go underneath the radical, treat that as the square root. Go here, do the square root here, that's 2. 2 times 3 is 6. So we have the 10 plus 6 underneath this radical. This is the square root of 16. Other side, square root of 4 is 2. And is the square root of 16 equal to 2? No, 4 does not equal 2. Okay, so x equals 4 is actually not part of our solution set. And so we want to do the same thing and check x equals 25. So plugging it in, we get the square root 10 plus 3 times the square root of 25. Is that equal to the square root of 25? So square root 10 plus 3 times the square root of 5. Sorry, square root of 25 is 5. So 3 times 5 is 15. Is this equal to the square root of 25? And already I can see that that is going to be true. Square root of 25 is equal to square root of 25. So we do have a solution, but it's only 25. So not too bad, right? Hopefully, let's see.
Miss Nossinger,
Yes.
wouldn't 10 plus 16 equal 26?
Yeah, so let me just make sure I did my math right. I think I might have done something wrong over here anyways. Because I'm looking at this, it should have been just 6, sorry. Because right here, this shouldn't have been a 16. This is 3 times square root of 4 is 2. And so this should have been 6. I think I was thinking ahead of my, while I was writing, which I do. And so the result of 10 plus 6 is 16. But this should have been 6. And you're right. With what I had, it would have been 26.
Just wanted to make sure.
Thank you. Okay, one more with radicals. If we had the square root and underneath that radical was 2x plus 3. And then outside of the radical, we have minus the square root of x plus 1. This is all equal to 1. Okay, so first step again, we want to isolate our radical or one of them. And so let's add the square root of x plus 1. And so doing that, we get the square root of 2x plus 3. This is equal to 1 plus the square root of x plus 1. So we've isolated one of the radicals. We're going to raise both sides by that index, which is a square. So the left-hand side is nice because that just clears and we just left with a radicand, which is 2x plus 3. The right-hand side, we have to distribute this out. So 1 plus square root of x plus 1, all times 1 plus square root of x plus 1. I'm going to need to distribute, so let's just bring down the left-hand side, 2x plus 3. So if we distribute 1 to each term, we get 1 times 1, which is 1. 1 times the square root of x plus 1, so that's plus the square root of x plus 1. And then distributing the square root of x plus 1 to each piece. We got the square root of x plus 1 times 1, so that's plus square root of x plus 1. And the square root of x plus 1 times the square root of x plus 1 is the same thing as the square root of x plus 1 squared, which just gives us the radicand, which is x plus 1. Okay, so I notice I can simplify that right-hand side a little bit, and I also notice that we still have radicals in that equation. And so bring down the 2x plus 3. This is equal to, so we have a 1 plus a 1, so that would give us plus 2, so 2. Here we have a square root of x plus 1 plus a square root of x plus 1. So when you're summing radicals, they have to have the same thing underneath the radical, and you just add the numbers in front and treat it the same, like it was x. So 1 plus 1, so this would be plus 2 square roots of x plus 1. And then we're still left with a single x, so plus x. So we're going to repeat the process. We got to isolate that radical. So how about let's subtract x on both sides here. And let's subtract 2 on both sides here. So 2x minus x, that would leave us with a single x. 3 minus 2, so that's plus 1, is equal to 2 square root of x plus 1. So either divide by 2, but we're going to have to distribute and stuff once we square. So I would leave it like that and deal with it later. So square both sides of the equation. So x plus 1 times x plus 1 is equal to square this 2. I get 4. I need parentheses here. And if I square the square root, I'm left with a radicand. So I need parentheses around that whole radicand, x plus 1. So if we distribute x plus 1 times x plus 1 and combine like terms, I hope you're okay with me skipping the step, you get x squared plus 2x plus 1 equals, now let's distribute the 4. So 4x plus 4. No more radicals. Determine the type, quadratic. Let's set it equal to 0 and see if we can factor. So if we subtract 4x on both sides, if we subtract 4 on both sides, we're left with x squared. 2x minus 4x is negative 2x. And 1 minus 4, so minus 3, equals 0. It does factor. There are two numbers that multiply to a negative 3 and add to a negative 2. So negative 3 and positive 1 multiply to negative 3 and add to negative 2. So x minus 3, x plus 1 equals 0. So set each factor equal to 0. We get x is equal to 3, and we get x is equal to negative 1. Go back, we squared both sides twice, and so now we need to check. So if we plug it in, you have 2, you see an x there, put parentheses, and then plus 3, and minus square root, you see an x, put parentheses, plus 1. Does this equal 1? I'm going to try something, maybe. Aha. Oh, I don't know if that was the best. I didn't want to have to rewrite it again and put in the 1, so I thought I was being, or negative 1, I thought I was being clever. Let me go back, okay. So now let's go back and what are we checking? We're checking x equals 3. Go back in and plug in 3 wherever you saw the parentheses in there. So we have the square root of 2 times 3 is 6, plus this 3 under here, so this is the square root of 9, minus, this is the square root of 4. Is this equal to 1? Yes, 3 minus 2 equals 1. So now plug in x equals negative 1. So plug in negative 1 wherever you see an x. So we have 2 times negative 1 underneath the radical plus 3. So that's negative 2 plus 3 is positive 1. So this would give us the square root of 1 minus, here we have negative 1 plus 1 underneath the radical, which is 0, and square root of 0 is 0. So 1 minus 0 is 1, and 1 is equal to 1. So both of the solutions work. So our solutions are x equals 3 and x equals negative 1. I have your textbook pulled up on a different computer so I can pull problems easily. What if it was, one more, this one doesn't have a radical, but it does have a power. So we inside parentheses, we have 2x plus 1 inside parentheses. And that whole parentheses is raised to the 1/3 power. This is equal to negative 1. So So we're going to use the rules. So if we let power to power is multiplication, so we want something that would clear 1/3 here. So if you multiply by the reciprocal of the exponent that's a rational, then that would give us 1. So if we multiply both sides by 3, or cube both sides, that would give us 2x plus 1 is equal to -1 cubed. Well, if you cube -1 times -1, that's +1. +1 times -1 is -1. So notice this is linear. So we solved that by isolating the variable. So let's subtract 1 on both sides. Shoot. And so we get 2x is equal to -2. Get rid of the 2 in front of the x. We can divide both sides by 2. So we get x is -1. Okay, so as long as I didn't make any errors going through my work in this, I shouldn't have to check it. What I've gotten should work. Because I cubed both sides of the equation, and it's not, 3 is not an even number.
Shouldn't you add 1 to both sides instead of subtracting?
If I was trying to set this equal to 0, I would have added 1 to both sides, but I'm trying to get this term by itself and its addition in here. So to cancel out, I'd have to subtract it.
Okay, got it. Thank you.
You're welcome. Yeah, so linear, we usually want to isolate the variable, get everything else to the other side. Quadratic, you usually want to get everything to one side and set it equal to 0. Okay. Maybe I should have you guys try one. And I want my pen to be bigger just because I like the thickness when I'm writing and I don't like it being really thin. There we go. Okay, so this is a try it. And you guys are going to try the problem. You have a 4th root. And underneath that 4th root, you have 5x squared minus 6. And then we have an equal sign, and that is equal to x. So see if you could solve that. So I'm just going to pause the video while I give you like 5 minutes to work on this and see if you can do it. Okay, so you guys had a chance to work on this problem for a little bit, and then we came back together and actually you guys walked me through this problem and how to solve it, and you guys did a great job. And so first step that you did was you raised both sides by the 4th power here so that you could clear this radical. Once you did that, you got everything to one side, you set it equal to 0. This looks similar to a quadratic in the fact that x squared times x squared is x to the 4th. And when we sum those middle terms, we'll get the x squared term here. So the two numbers that multiply to 6 and add to -5 are -3 and -2. And then from this piece, we can set each factor equal to 0. We decided to use the square root method by adding 3 to both sides and taking the square root of both sides. So we get x equals plus or minus √3 there, and x squared minus 2 equals 0. Add 2 to both sides, take the square root. So we get x equals plus or minus √2 here. Because we rose both sides to an even power, this is where we had to go back and check. These were some of the solution ideas that people had given before we started to do this problem. And so we went back in and we checked, we were okay with √3. The problem is with this negative √3, when we plugged it in, we'd have a negative here and everything would cancel down, but we don't get √3 equals -√3. Same sort of idea, when we plugged in √2 here, it ended up working, but -√2 would not. And so we do have 2 answers, √3 and √2. Okay, that was a really fast explanation of what we had done. But you can always go back and re-listen or pause and kind of digest what I was saying after each sentence if you want. Okay, let me stop the video and then we're gonna get into it, like I just said, a new portion of the same section of this textbook, which is solving quadratics or quadratic in form.